Okay. Okay. Hello, everybody. Out of curiosity, are there people not from Montreal who got this this webinar link through the SpaceTel Masterclass links, for example? Just out of curiosity. Okay, no one. Good. So we're mostly Montreal people. So I just sent an email with a link to the slide package. Thanks for attending today's workshop. I'll go into presenter mode in a second. Okay, I'll share my screen. All right, so I'd like to acknowledge the tremendous help from Geert-Jan Tallens and Neil Cook here, who helped developing these slides and some of the exercises. And also Alexandros Marakoudakis, who's a University of Western Ontario postdoc, who's attended James Webb Masterclasses. You can, by the way, interrupt me anytime if you have any question. I'll be presenting slides, general presentation for about an hour, and then Alexandros from Western will take over for some demo of the ETC APT and Jdox. And then that should bring us to lunchtime. And after that, we'll go through some slides about 3 different modes: the TSO mode, the IFU integral fill unit modes, and long slit spectroscopy. So, of course, Montreal, we have a big interest in TSO, but also there were requests, or people showed interest in long slit spectroscopy and IFUs as well. So we're trying to cover as much as we can there. And the idea in the afternoon is that you'll go on and try to do the exercise on your own, and we'll have the line open for questions and answers. All right. Okay. So that's the plan for today. A presentation about the James Webb Telescope. Starts with key facts. It's the proposed launch date is still March 30th, 2021. The mission duration is 5 years nominal, and perhaps 10 years. It's a 6.5 meter telescope with 25 square meter surface area. It has a very good angular resolution that depends on wavelength essentially, but 0.1 arc second at 2 microns. It covers, so it works in the infrared, covers from 0.6 to 28 microns. And it will be positioned at the solar Earth L2 point at 1.5 million kilometers. So it has this big sun shield to keep the instruments cold on the night side and the electronics warm on the sun side. So you see that the temperature, so all instruments will be cooled passively to 40 K. And the MIRI instrument, the mid-infrared, will have an additional cryocooler to cool it even further down. And you see that the electronics box is on the warm side at 300 K approximately. On the right, you have the field of regard. So the region on the sky that the telescope at any given date can point to. It's about 40 degrees. 40% that is of the full celestial sphere. I'll give more details a bit later. Okay, here's the, so we'll talk a bit about a brief overview of the instrument modes. And I start here by showing you the focal region, the focal plane of the observatory. You see that instruments are a bit off-centered here, with NIRCam, the imager the closest to the center with the best optical quality. You have NIRIS on the bottom right, you have MIRI on the very right, and NIRSpec on the left. Let's start with the mid-infrared instrument MIRI. Okay, it provides both imaging and spectroscopy. Between about 5 and 29 microns. It has imaging capability. If you look on the right-hand side, you see a 74 arc second wide by 113 arc second. That's the imaging part of the detector. So it uses 10 filters, and it has a low resolution spectroscopy mode as well, called the LRS. That covers between 5 and 12 micron at a low resolving power of roughly about 40 to 200, depending on the wavelength. Also, there's the MRS, the medium resolution spectroscopy mode, also called the IFU, because it is an integral field unit, and we'll give more details about that at the beginning this afternoon. So the IFU unit uses 2 separate detectors, not shown here, but the field of view of the IFU is the small orange box here. So that's the field of view of the IFU, and it's imaged on 2 other detectors not shown. And there's also coronagraphy mode with MIRI. It has 4 different coronagraphs, and we will not go into any details about that today, but there's plenty of information available. All right, so that's for MIRI. And here we have a zoom of what I was talking about the imager field of view and the 4 coronagraphy spots and the MRS on the right side. This is the MRS, in a nutshell. It's so on the left you have the footprint on the sky of different wavelength channels. The small squares, the field of view of the short wavelengths, and the red is of the reddest wavelengths. So they don't exactly have the same footprint on the sky, and each of those footprints gets split into small slitlets, and spectra are projected on 2 detectors. That's shown in the middle with channel 1, 2, 3, and 4. And those are the spectra of the IFU on 2 detectors. And on the right, It's a schematic to tell you that you can observe all across the 5 to 29 microns with 4 channels and 3 sub-channels. It's a bit complicated if you're new to this, but essentially you can get the full wavelength coverage by taking 3 separate exposures. We'll come back to this. Okay, so now NIRCam, which is like a workhorse instrument, has 10 simultaneous detectors observing. So it can do obviously imaging between 0.6 and 2.3 in the blue channel and 2.4 and 5 microns in the red channel. So I think I've got this here. So so the blue squares are detectors, short wavelength detectors, blue detectors, and the red squares are red detectors, so sensitive to between 2.5 and 5. So you see that you have, you know, in total 8 blue channel detectors and 2 red channel detectors. And so that's to basically match the full width f max of the PSF at different wavelengths, and otherwise the field of view overlap between the red and the blue channels. So with NIRCam, you can also do wide field slitless. I'll come back to that. You can do wide field slitless spectroscopy in the red part of the near infrared, and that's achieved at a resolving power, pretty high resolving power of about 1600. You have coronographic imaging with the green boxes on top here, and spectrophotometric time series as well, although we will not talk much about that mode. Okay, then you have the NIRSpec, the near infrared spectrograph, and that's a spectroscopy machine. It has multi-object spectroscopy with the microshutter assembly, the MSA. It can also do integral field unit spectroscopy. So let me see what I got here. Yeah, so you have here a figure that shows on top you have the blue MSA. So that's the masks and the microshutter assembly through which light goes and goes through some more optics, and in the back you see the 2 gray detectors actually where the images are projected. So the MSA contains 250,000 shutters, and you know they work great, except there's a few failed open and failed closed shutters that you have to manage with. And there's a great NIRSpec observation planning software to help you manage that. Unfortunately, today we're not going to talk about that, but there's it's a whole word in itself to cover this feature for James Webb. You see on the very left the field of view of the IFU of NIRSpec. So if you are doing integral field spectroscopy, the light goes through this square box and then goes through a splitter that and then through gratings, and it's projected on the detector. Then there's our favorite instrument, right? In Canada, the Canadian made instrument NIRIS. It provides slitless spectroscopy, high contrast interferometric imaging, the AMI mode, and also imaging between 0.6 and 5 microns. So the WFIS, the wide field slitless spectroscopy, is complementary to the NIRCam feature. So it can do wide field slitless in the blue channel and at a lower resolving power of 150. We'll talk about the single object slitless spectroscopy mode, of course, that can do time series between 0.6 and 2.8 microns. And there's the AMI interferometric mode that cannot use 12 filters covering the wavelength range. It actually can use 3 filters or 4 filters. That's a mistake. finally, the FGS, the fine guidance sensors, 2 detectors that provide the fine pointing required to integrate for long exposure with James Webb. It has a guiding stability of the order of 6 milliarc seconds. So that's you know, 1/10 of a pixel of a nearest pixel. That's pretty good. All right. So the next step is about exactly that, guiding and the visit splitting distance. That's a concept that will come in the astronomer proposal tool, the APT. If you've encountered this or used it before, you know that there's this visit splitting distance concept. Well, it boils down to this. If you look on the sketch on the right, whenever the telescope slews to a new target, there's a guide star acquisition. And the FGS tries to pick a guide star that's near the center of the array. And if you're near the galactic plane, then you have plenty of stars, and the chances are that you're going to be able to find one almost exactly at the center. Near the pole, there's less stars, so you might find a guide star a bit off center. Anyway, the visit splitting distance is this red circle, and it's essentially, you know, how far you can move or do small dithering without losing the guide star. And that defines a visit in the APT. And so anytime that you lose a guide star because you're moving too far, you go over the visit splitting distance, and then you need to reacquire a new guide star, and that takes additional overheads. So that's why in the APT, they split all your observations into, you know, into visits as soon as you go above the visit splitting distance. So in a typical visit, you slew to a guide star, and so there's that is included in the visit. You have the instrument overheads in the visit, so the guide star acquisition, target acquisition, the small angle maneuver, so the dithers, and the science exposure. So those all are in a visit. All right. For many modes, James Webb will use target acquisition. So you'll have in the exposure time calculator, you'll have to you know, look at the target acquisition exposure, and in the APT you'll need to feel what kind of target acquisition you're using. And so that's because the observatory can slew to a precision of about, say, 10 arc seconds based on the star tracker, and based on the gyroscope precision. And so if you need more precise position, say on slits or on the sweet spot for the sauce, then you need the target acquisition, and that's required for AMI and SOS for NIRIS, for near-spec multi-object spectroscopy, long slit, TSO, IFU, although you can also opt out of target acquisition for a few of those modes. There's for near-cam chronography, you need the target acquisition for TSO as well, MIRI, LRS, MRS chronography. And as you can imagine, for the near-cam and MIRI imaging modes don't require target acquisition because they have a wide enough field of view. And same is true for NIRIS, near-cam WIFIS. All right, in terms of the overheads that are charged to you, and you'll see that in the APT, there are different sources of overheads. You have the filter wheel movements, dither, you have the target acquisition, you have the slews to the target, the guiding. All of this counts as the instrument overhead, and you'll see it as that in the APT. So on top of your visit, on top of that, you have the so-called indirect statistical overhead of 16%. So a tax, essentially you take all of your science time plus overheads and you multiply by 1.16. And that's to account for like the calibrations that the James Webb project needs to do, and the ground communication to download data, and the phasing of the mirrors. All of that was estimated and to be about 16% over the life of the telescope, and that's what you're charged. And so the requested time in your proposal will be the slew time plus instrumentation overhead plus the science integration, and that multiplies by 1.16. Okay. Good thing is that James Webb allows parallel observations to be more efficient. So there's a few offered parallel modes, and not all possibilities are offered. Keep in mind that two instruments cannot, of course, observe the same target at the same time because they are at different position on the field of view. So you have two types of parallel operations that exist. You have the coordinated parallels. Those are, you have a proposal that will explicitly use both or two instruments for their same or similar science goals. And so in the proposal, they will have to justify the use of both instruments. You also have pure parallels, which are interesting. Those ones are, programs where the PI would have only used one instrument, and you as a proposer, you can ask for another instrument piggyback on that program and use other instruments at the same time. Of course, there are many constraints when you use pure parallels, but know that it's a thing that you can use. You have here the tables of possible instrument combinations. So here you'll see, for instance, that nearest imaging is allowed. So maybe I went over this quickly at the beginning, but nearest imaging is a possible mode, but that's not offered as the main instrument. It's only offered as a parallel instrument to complement, say, NIRCam imaging and NIRCam WFIS. And so you see, and they are, I think they are still planning to add a few more options, a few more combinations of parallel modes. Currently, as a side note, currently there's no parallel mode when you do TSO. TSO prevents any parallel observations to happen. And that's because that's based on worries that maybe, other instruments may disturb the stability required for SOS or for TSO. Maybe eventually it could be lifted. Who knows? For cycle one, that's a constraint. All right. So pointing of the telescope. It's important here to understand what's happening, just to understand how your targets are visible throughout the year. So the telescope on the left has some freedom of about 40 degrees of solar elongation. It can tilt a little bit by about 40 degrees. And you obviously don't want to expose any part of the telescope to direct sunlight. So that's why it's limited. On the right, you have also a limited field rotation freedom of about 10 degrees, and for the same reason. So those two freedom give you, the constraints, and so the field of regard, the region here in colored on the celestial sphere, is where the scientific observations can be conducted safely at any given time. And that field of regard, as the observatory orbits around the sun, moves by about 1 degree per day on the ecliptic longitudes. And over time, this annulus sweeps over the entire celestial sphere. And at any given time, you observe about 39% of the full sky, but over a 6-month period, you can have access to 100% of the celestial sphere. So over the course of 1 year, one cycle, you usually get 2 windows of observability for any given target. Of course, if you're near the ecliptic pole, then you can have even constant viewing possibility in the small 5-degree regions around both poles. So here's the James Webb Coordinate System. You keep this in mind when you'll do your APT. So if the celestial sphere coordinates is the red arrows here, and you see the field of view of the instrument, and the V3 axis is defined here as the blue arrow. And that's the V3 position angle, the observatory position angle, all right? And if you look at two different dates, this system will rotate over time and make a full circle in 1 year. And so you see the instruments follow the same. So if you look at each individual instrument, there's like a aperture position angle that's defined. That's the blue arrow for each instrument. And you see that NIRCam, NIRISS, and MIRI are more or less pointed the same way as the observatory V3PA. And same for FGS. And NIRSPEC is the only one that's really different. It's 138 degrees away from the observatory position angle. So in terms of definition that will be used later in the APT, so you have the aperture position angle, which is each instrument position angle, and you have the V3PA, which is the observatory position angle. And you can use either ones as constraints if you want to constrain your position angle for your observations. Okay, so actually, when do you need to constrain the V3 position angle? You have to keep in mind that if you do so, if you constrain your position angle, then it narrows your scheduling opportunity. Okay, so usually for many targets, there's two visibility periods throughout the years of, say, roughly a month each. And if you narrow the PA, if you want to have your observation set at a defined PA, it could narrow it to a few, maybe a week on each window. So why would you still want to do this? Well, for example, for NIRISS TSO, some PA cause too much field contamination, and you have to verify this with the contamination tools, either in Pendix or on the UDM page. We'll get to that later. The NIRSPEC MOS, multi-object spectroscopy, also needs to fix its PA for positioning of all the open slitlets. So that's a requirement. If you want to do mosaicing in imaging modes, say you want to cover a large extended galaxy or perhaps a deep field, and you would like to fill all of the tiles properly without gaps, then you probably need to fix your PA so that all the tiles are aligned to each other. Another reason is chronography. Chronography uses masks and which have a small, like spider-like feature, and so if you unfortunately choose a bad date, the planet that you're interested in may lie behind those spider arms, and so that's one of the reasons you'd like to constrain the PA for chronography. Okay, another topic, sky background. You have to know that for imaging and spectroscopy, especially in the mid-infrared, the sky background may be is important to consider as you go beyond, say, 4 microns. That's important to consider. So on the left, you have the flux as a function of the wavelength coming from the all sources of background. So in blue is the zodiacal light, and so that's from scattered light, sunlight scattered by the dust in the solar system. And in red you have the thermal emission of the observatory itself, and in black is the resultant total background. you see it rises quickly at about 4 microns. On the right-hand side, you have a plot of the intensity of the Zodi light as a function of time. Because if you think about it, if you are interested at one object in the sky, depending when you observe it, you may go through more or less dust from the solar system. And that means that there are times or in the year where the Zodi light background contribution is a minimum, and you have time when it's higher. And so in the ETC, this is how you set, you can set in the ETC if you want to consider a low, medium, or high sky background, and that's essentially the reasoning behind. If you choose the very low, that means you're close to the minimum, but then you limit your observability window. And if you allow high, that means you could be in any of those cases here on the curve. Okay. So no questions so far. Everything is smooth. You can all hear me. All right. So let's talk about detector readout schemes and the exposure time. If you're not familiar with infrared detector technology, this may come as a bit of a weirdness if you're used instead to CCD in the visible. So obvious things that are actually important to know is that none of the instrument on board James Webb has a shutter. So the integration time is set by how fast an image or a frame is read out. Okay, so you read each pixels consecutively. They take about 10 microseconds per pixel, and so you can read all of the pixel in a certain amount of time. That's the frame time or a read time. And every time you read pixels in the infrared detector, the charges are not lost, so the readout is non-destructive. So the charges simply accumulate, and you read the level that they're currently at whenever you read. And so there's a bit of a James Webb jargon associated with this. It's coming throughout the ETC and the APT, so that's important to get familiar with. I'm sure, okay, I'll go over it now, but I'm sure you'll have to come back to it if you're not familiar with infrared technology or James Webb jargon. But so whenever you want to start an exposure, you do a reset. So it's possible to reset the charges to 0. And immediately after you've reset, well, charges start to accumulate, and they will accumulate until you do another reset. So an integration here will spend some time, and throughout the integration, you'll read out frames repeatedly at a constant rate. Okay, and so a frame is really a full read of the full detector, and they come just as you finished reading one, you start the next frame, and so each dot circle here is a frame readout. And James Webb, for reasons of essentially data volume, to limit the data volume, has arranged to make groups of those frames that are average on board. On board, they average, say here, 4 frames together, and they will call this a group, and they will only send to Earth the result of the average. Okay. And you can also have skipped images. Those are the red points. And so you see that in this case, the integration here consists of 3 groups, okay? And each group is 4 frames. And after you've reached the top of your integration, you reset and you start another integration. And when you put all the integration next to each other, that's called an exposure. And an exposure is what you'll get when you download your data. As a scientist, you'll get FITS file, and each FITS file is an exposure. And so an exposure can contain, in this case here, 2 integrations, but it can contain more than that. In fact, for the TSO observations, say you have a 4-hour observations, your entire data will come in principle in a single FITS file that will contain hundreds of integrations. Okay. It may actually be broken down in like 2 GB chunks, but the concept is the same. A single exposure is a single FITS file in a sense. There's no interruption between different integrations as well. Okay. The result of an integration is that you actually fit the line, okay? And so the flux you get in the process data is a linear fit to the flux versus time integration. And so you can imagine that you can improve the SNR if you have a large number of groups here. If you have a short integration, only a few reads, then your SNR may not be as high. So that's where. Yeah, I'm hearing someone. Does anyone have a question?
Why? What are they saying?
Someone's not muted.
Okay. That's where strategy to set your N groups is important. If you're observing a bright target, then you're in a regime where you're photon noise limited, and what you should watch for is saturation. You know, so you should use the number of groups that will prevent saturation. Whoops, sorry, I want to come back. So you'll have, say, N groups of, you know, less than 10, perhaps. If you're observing a faint target, then you're in a readout noise limit. And in this case, you need to maximize the number of groups per integration. But with some limits that, you know, here, each instrument recommends slightly different limits, but here, NearSpec recommend an integration that doesn't last more than 1,500 seconds. Mary is about 1,000 seconds, and NearCam and NearIS is, you know, between 15 and 30 minutes. If you go beyond this and have too long integration, what happens is you don't saturate, but you have lots of cosmic ray hits, and they will contaminate a larger and larger fraction of your pixels, and so you don't want to get in that regime. All right, okay, let's see if that will work. So if you've not explored too much James Webb, and you have an idea for a science project and would like to know, you know, is it feasible or not? There's a quick tool that you can use. It's called JWST, and it will allow you to give you some signal to noise ratio for imaging in a quick way. So let's see if that works. Okay, so that's just, it came out because if you've used the ETC, it's a bit complex to set up. And this is a more quick way to get some of the answers. So you can select, you know, your favorite mode and use, you know, a target magnitude that you want, and you see in the plot here, you see the signal to noise ratio as a function of, you know, for the different filters in this case. You can get a quick estimate of if your science is doable, and you can adjust the exposure time. Okay, you can even use the spectroscopy mode. Okay, so yeah, so that gives you a quick and easy way to assess whether your favorite target is observable. You cannot adjust, for example, the you know, the photometric aperture that you're going to use, and all of, you know, the sky background that you may perform in the MIRI. And so if you want, you know, more accurate results, you'll need to go through the ETC.
But is it possible to export this from the JWST?
Good question. I guess it is. Save here.
Okay.
Yeah.
Oh, that's an image. Okay.
It's an image. Yeah.
Okay, that's fine.
Yeah. I haven't used that much myself. All right, we're coming to an interesting part. It's about the call for proposals and policies. So here's a timeline of the project. So we're March 18, and the deadline is still May 1st. I don't think it's going to move. Who knows? And the TAC, the cycle 1 TAC, is scheduled to happen at the end of July for 2 weeks. I'll give you more details here in a few slides. Launch March 2021. The cycle 1 starts about October 2021, so 6 months after launch. And here what's not shown is that the TAC result will be announced, I think it's in mid-August 2020. And note here that the cycle 2 deadline is just 3 months after the start of cycle 1. So very, very shortly after the start of cycle 1. So if you plan on submitting a cycle 2 proposal based on existing data, you have a very short time to obtain and analyze the data. Otherwise, you're in the same boat as for cycle 1, based on best estimates rather than actual images. All right. So SpaceTel anticipates receiving well over 1,000 proposals. It's expected to award about 300 successful proposals after TAC and panel review for about a total of 6,000 hours of observing time. That includes about 2,000 hours of oversubscription to maximize the observing efficiency and fill gaps between observations. And so, so this 2,000 extra hours in principle will overflow to the cycle 2 if they're not observed in cycle 1. Here's a list of the categories under which your proposal can fall. So you have small, medium, large, and you have additional subcategories that I will not go into details here, but we'll mostly concentrate on the difference between small, medium, large. There's a different archival proposal category that applies to US-based PIs, because that allows them to get some funding from NASA using existing data, either GTO or ERS data. But the Canadian Space Agency should announce financial support for accepted proposals for Canadian proposals also, but it's not yet official, but they should announce that we could also get funding for archival proposals. I mean, this early in the mission is a bit like of a stretch to ask for archival, but in a later cycles, it may be actually very handy. Okay, so the different proposal sizes, you have the small, that's less than 25 hours. There's 3,005 hours for that available. And so if you do the maths, that means there should be more than 140 programs, probably even 200 to 250 small programs accepted. There's a medium-sized proposal, 1,500 hours, that should amount to between 20 and 60 programs. The large proposals, very few of them are going to be selected, maybe less than 10 for 1,000 hours total. And something to think about when you write your proposal is that small, medium will be judged differently than large. The small, medium will be reviewed by each topical panel, and I will come back in the next slide what that is. And the large will be reviewed by each TAC chairs, and they will form a panel. The chairs will form a panel, and they will judge for those large proposals. So the topical panels are actually your science field. There's 8 of them. Okay, so from cosmology to solar system, and you select which panel you land in the APT by selecting the scientific category here. So this may sound like not very important, but you actually are, by selecting here, you're selecting which TAC you're going to end up in. And the science keywords here will determine which reviewer in each topical panel gets assigned your proposal. Okay, so you have a variety of reviewers in each topical panel, in each TAC, and they will review, they will have to review proposals according to the science keywords that you've attributed to your program. So pick those carefully and meaningfully. The proposal review process is the following. The TAC review will span 2 weeks. The week 1 is for galactic, week 2 extragalactic. Each topical panel will meet from Monday to mid of the week to review the small and medium proposals. And so that's most of us, right? On the call, I suspect most people will write a short, small or medium proposal. So you need to write your proposal to have a broad appeal to all people in that topical panel. Then the panel chairs will review the large programs on the second half of that week. So they have the same amount of time to review the large proposals. After acceptance of your proposal, we'll require a technical review, and most reviews will take place in late 2020 to prepare the cycle 1 long range plan. You may be aware that the dual anonymous system will be used for your review. So we're all familiar with single anonymous proposals. That's been the case forever. Basically, you don't know who the TAC is, but now the TAC does not know who you are when they read your proposal. In fact, they literally don't see your the list of authors, and they don't see the team expertise section as well. So they have no clue who you are unless you give them some clues in your text, and you're not really allowed to do so. They strongly suggest that you try to anonymize your writing style, and the reason they're doing this is, you'll guess, is because it's to limit initially the gender biases, but also it's come to be also to limit any kind of bias, like selecting good reputation institutions in large group over small institution and small groups, for example. And that's been working well for HST for 2 years now, two cycles. And so that's what they are gonna use. And here we have examples of do's and don'ts. So don't say my successful HST program, blah, blah, blah. Say rather the HST program go, blah, blah, blah. Our analysis presented in Doe et al. No. Analysis by Doe et al. Blah, blah, blah. So, yeah, you need to stay anonymous. And there's been a few cases where HST proposals have been rejected based on because they were not respecting this guideline. So the review in this way is based on scientific merit only, not on people. In each TAC, there's a person, a leveler, that's present in the room to help ensure that the guidelines are respected. So the TAC review proposals without seeing author names nor team expertise section. And after ranking though, those can be revealed if the TAC wants to see it. So after the ranking, the scientific ranking has been done, you could access, the TAC can access your name and team expertise and downgrade your proposal if there's a blatant problem with the authors or the team expertise. So you can go at this link to have more details if you're interested in. Something you'll need to do for your proposal, and mention it in the science justification, and you need to check for duplication. So the GTO teams and the ERS have observations out there, and you need to make sure that you're not observing the same target. And so how you define a duplication is basically target-based or field-based, and but also observing mode and instrument-based. And if you have the same exact target, the same mode, but say 4 times the integration time, then that can start to be considered not a duplication, okay? But if you're close in integration time, that's a duplication. Checking that is your responsibility, and you can have information about how to check for duplication in Jdox. And you can also check it on the MAST archive. So let's see if that will work. I will go on the MAST archive and check for existing programs that, so all the GTO and ERS programs are, already on the archive of James Webb. Of course, there's no actual observations, but all the targets are defined, all the fields. So you can check there if your favorite object is already observed. Okay, so if I have an object, say M51, that I'm interested in, do a search. So is M51 going to be observed with James Webb? We'll see the results. It takes about 10 to 15 seconds. Okay, I'll do already another search on another object and come back to M51. So M51 here is a list of all observations archived. And if you show all of the mission, you see that there's nothing associated with James Webb. So funny enough, M51 is not planned to be observed by any GTO team, okay? If you look at the 30 Doradus star, then, and you expand on all the science mission, you see here James Webb. So there's some observation of that star, in fact, with near spec. Okay, so with this grading, so stay away from this exact observing mode, and you should be okay for duplication. All right, and all those are the two screenshots of the same thing. Now a few slides about tips to help you for the proposal. Okay, they come from Antonina Nota, Associate Director of ESA at SpaceTel, who has participated in such TAC panels, many of them. 5 things. So JWST proposals are complex. Start early now. Okay, I think that's pretty clear. You have to start now because it's complex. Get familiar with the documentation, Jdox, the call for proposal guidelines. Comply with dual anonymous guidelines. In your writing style, make it easy for the reviewers to review, and write your proposal for astronomers, but not necessarily experts in your field. So those are, make sense tips, but yeah, good to remind you. There's additional and a non-exhaustive list of tips that I came up with. So if you start on the left in your technical justifications, do you have any special requirement in the APT? If so, justify why. Is there any remaining warning in the APT? If so, justify. Why can't you do the same science from the ground or with another observatory? Why in cycle 1? Why use this instrument mode rather than another one? Are you impacted if cycle 1 starts later? So you could preemptively describe mitigations in that case. Is there duplication with existing GTO ERS observations? Actually, you need to mention that in the science justification if there is. In the science justifications, you have do's and don'ts. So you have to state what you're doing in the first paragraph, watch anonymity, give proper credit for discoveries or ideas, proofread. So Ideally, you'll hand over your proposal more than a week in advance to someone who's never read it, and you'll get a nice review. Make sure there's a big picture explanation. Include enough information in figure captions. Close with a summary section paragraph. Okay, and don't use abbreviations without explanation. Don't throw shade on colleagues or projects, and don't go too deep in the details of your own field. So many tips that make sense, and probably you already have this in mind. And that brings me to the end of my first hour of overall presentation of the observatory. So it's, what is it, 10:27. Okay, we're actually on time, but maybe a bit early at this point already. So what's coming is Alexandros Marakoudakis, who's going to present from Western Ontario some demo about APT and ETC and Jdox, but that starts at 11. Okay, so we have maybe almost half an hour already for if you have any question, and or otherwise we'll take a break until 11. So I'm leaving the line open, and please, if you have any question at this point.
Just to add in, we also have the Google spreadsheet. So if you don't want to talk out loud, or if you think of a question in between, or one that you think might be a little bit too complicated for an online thing, please add it there. We'll also have Space Tell on the line between 3 and 5. So even if we can't answer the questions, they can. So please try and fill it out. I put the link in the chat, but if you have problems editing it, let me know.
Okay, that's a good point. So let's see in the chat window. Thanks, Neil, for that. Forget how. Oh, there. Okay. Okay, I'm looking at the list of people online at this point, and I'd like to know if any of you is actually interested in long slit spectroscopy and IFU here, because I see mostly TSO interested people. So maybe raise a flag or mention it in the chat if you're interested in long slit spectroscopy and IFU. Oh, Alexandro is there. Hello, Alexandros.
Hello, can you hear me?
Yes. How
Great.
are you doing? How are you
I'm
doing?
good.
Good. So I hear that you're back at university today for this, right?
Right.
Okay, thanks a lot.
No problem.
Yeah, are you ready actually to present, or you want to wait until 11?
Yes, I can start at any point, so just let me know.
Okay, so okay, boy, I hope no one is left. Let's see, how many people do we have? It feels like they're almost all people are still online. So I would say, Alexandros, if you're good to go, then I invite you to start.
Okay, I can do that. I will start sharing my screen, and please let me know if you can see that. So,
Okay. I'll stop share my.
Yeah. So let me know if you can see that.
Yes.
Okay, that's great. All right, so we will be looking now the JWST resources and main proposal planning tools. So we will start with the user documentation pages, or Jdox. You can find this page if you simply search in any search engine, just type JWST and Jdox, and it should lead you here. So Jdox is basically a large collection of articles about the telescope, the instruments, the different observing modes, the proposal planning tools, as well as articles for the calls of proposals and policies. And the overall idea, the overall philosophy that the articles are written is follow a Wikipedia-like every page is page one philosophy. So this basically means that these are short, focused, and well-linked articles. And in each article, you will have a topic sentence at the top, which will describe the basic content of a given article. Okay, so there are many articles on Jdox, and it's really important to know how to navigate and how to find the articles that we're interested in. So I want to talk about three main navigation points. The first one is the quick links on the top. So if we go there, we will see that we have a section that describes the late breaking news about James Webb. We can also see which are the articles that have been updated lately on Jdox. There's a section with links to YouTube videos that contain tutorials and demos on how to use certain proposal tools and observing modes. There is also a pocket guide that is basically a small PDF that contains all the main information for the instruments and observing modes. And for people that like working offline, there are the PDF handbooks, which are essentially very large PDF files that contain all the articles that you can find on Jdox. There are also many acronyms related to James Webb, so you can find a description in this section over here, and you can also access the help desk from a link provided in this section here. So this is the first starting navigation point. And the second and probably most obvious navigation point is the side panel on the left, where articles are grouped into certain sections. So we have like the first section is the proposing opportunities with articles discussing about the call for proposals and the policies. We have the proposal preparation section, which has a really useful getting started guide and a few other important articles that I will discuss in a bit. We have the section with the different proposing tools. The two main tools are the exposure time calculator and the astronomer proposal tools. We have a section for the different instruments. And by the way, each time you see an arrow like this, it means that if you click, you can expand this and see all the subsections and articles. So you have the section with respect to all the instruments. And finally, you have a section about the data, how to obtain and understand data files. Okay, so this is the second navigation point. And the third, which is really useful and really important, is the advanced search at the top. So in this search field, I can start typing keywords about articles that I'm interested in. Let's say I'm interested in MIRI filters. And as I type that, articles would start appear over here, and I can find, the closest one to my search. Otherwise, I always have the option to hit enter, and this will take me to the advanced search results, where I can basically see that there are 600 articles related to these two keywords that I used, okay? And I also have the option to filter out the results and get exactly to the articles that I'm initially interested in. So again, just to summarize, we have the quick links, we have the side navigation bar, and the advanced search. All three are really useful. Probably you'd start with the first one, going to the second, and ending up to the third one. Okay. So now we know how to navigate and search for articles in Jdox, but I would also like to talk about 4 important sections that we always need to keep in mind. Okay, so we have a section that's called methods and roadmaps. So if we're interested in a given observing mode, there's specific roadmap designed for it. So let's say I'm interested in imaging, I can click in the roadmap section for this observing mode, and you can see there are different steps and in each steps, there's a collection of articles related to a given step. So we have an idea to how to proceed and plan our observations with a given observing mode. The second important thing I want to mention is that there's a section with example science programs. So if we click there, we will see that there are example programs that are sorted by instrument, okay? And you can see there are also a reference number that is really helpful, that we'll discuss about it in a second. So let's say I'm interested in doing MIRI MRS observations. There's an example for a late M-star. It might not be exactly the science case that I have in mind, but it's really useful to go through all the details in these proposals that are similar to ones that we're planning to do, because there are steps again, detailed steps, and it's really good to know what is the thought process we need to follow to design our own proposals. And also another important thing is there are step-by-step guides on how to determine and do all the details in the exposure time calculator, as well as the ABT. And there are also, we have access to the workbooks of the ETC and the ABT files for these specific example programs, and we will see how we can access them respectively when we are at the ETC and the ABT. Okay, so again, this is a really important thing to keep in mind. Example science programs sorted by instrument, which is good to have a look before starting on our own proposals. The third thing I want to mention, and this is basically what Loic mentioned before, that before we plan our observations, we want to make sure that the target we intend to observe with a specific instrument, observing mode, and configuration is not already scheduled to be observed in one of the GTO or ERS programs. So that's why we have the duplication checking, and you will find the link that Loic provided in his slides for the MAST data discovery portal. The last thing that is really important to keep in mind is that except from the ETC and ABT articles, you can find link to other tools. So there are also other tools that will help us plan our proposals. There are additional proposal preparation support tools like the JWST target visibility tools. There is the general target visibility tool. There's one for moving targets as well as choreography. There is a tool dedicated for background to estimate the background contribution in your observations and so on. You will find tools for simulating JWST performance, also external tools that were not designed by people at the STCI, but they are using that. Some examples I'm sure you will see later today is the Exoplanet Toolkit and Pandexo. Okay. And probably I will just summarize the main topics here again. We have 3 navigation points: the quick links, the sidebar, and the advanced search. And things that you want to keep in mind is that there are available roadmaps, example sign programs, and it's also important to do a duplication checking. We don't have to go and look at all the individual GTO and ERS programs and see if the targets we're interested are there. We're just going to use the mass database and find out. And lastly, keep in mind that there are other tools that can help us prepare our proposals. Okay, so now we will move on to the EDC. Again, we can find the EDC website using any search engine just by typing JWST and EDC. Okay, so this should lead us here. This is the main page where we have the option to work anonymously, but that will prevent us from saving our workbooks or sharing it with our colleagues. So it's always better, preferable to log in using the MyST account we have. So I will do that just now. And the first box on the top here is the box that will contain all our workbooks. It's going to be blank if we never used one before. Otherwise, it should be full with all the workbooks that we have worked with before. So we have the option to load, copy a workbook or remove it. And here we can create a new workbook. We can also access sample workbooks for specific strategies in observing mode. And here you will find the example science programs we mentioned before. And you can find them based on the ID number or the proposal, the science program name, okay? And you can click on those, load these workbooks and see how they prepare, they plan their exposure time parameters, okay? So, and on the bottom here, you also have the option to share your workbooks with colleagues, just you need to enter their email address. So we will start by creating a new workbook from scratch. It should appear here at the bottom in a few seconds. Yep, here it is. I will just go ahead and load it. So this is the main interface. There are basically 4 tabs. The first one is where our calculations will be performed. The second one is where we construct our scene and we define all the parameters for our sources. The third one is in case we have a spectrum for our object and we want to use that in the EDC, we have the option to upload it. We will talk about it in a second. And the last tab basically describes caveats and limitations with respect to the EDC calculations. So before performing any calculations, we should first define our scene and sources. Okay, so there are basically 6 sections in this tab. The first one on the top left is where we define our scene. And by default, when we create a new workbook, a new scene, and a new source will be created. And you can see that this source with ID number 1 is already assigned to this scene. So I can visualize my scene and sources on this section at the bottom. Right now it's blank because I have not selected my scene. Once I do that, you will see that the object that is within the scene appears, but it's grayed out. And the reason for that is that I have not selected my object as well. So once I do that again, you will see now it turns yellow. And this is useful because typically we can create complex scenes where we have many sources in it. And we always want to know which is the active source in which we define all the characteristics in the source editor here, okay? So it's really easy to create a new source. We just click here on the new and a new source will appear here. And this source, we need to associate it within a given scene. So if I wanted to place that in scene 1, I should select the source, I would select the scene, and I would add source. And you can see now that both sources 1 and 2 are assigned to this specific scene. Right now, I cannot see which one is source 1 or 2 because by default, when creating a new scene, it is placed at the very center of our scene, but there are options to create offsets, and we will see that later. The same way we are able to add a source, we also are able to remove a source. We just make sure we're highlighting both options and click on remove source, okay? So I will go ahead and discuss about the source editor, which basically we define all the characteristics for our sources. I will start with the ID. If we have many sources, it's good to give them an ID and be able to distinguish them. So here I will give an example. I'm going to be observing, let's say, a star-forming galaxy. So I will name that star-forming galaxy 1. And I will need to save that to take effect. So once I do that, the source name will be updated over here. The next tab is where we define the continuum. The first option we have is to use an uploaded file. So again, if we have available a spectrum for the object we intend to observe, we have the option to upload it in this tab here, the uploaded spectra. So once I click there and I'll go down to the bottom of the page, I can see I can choose the file here. I will not do it right now, but I can choose the file and then hit upload, and the spectrum will appear on the box over here, okay? One of the things I did not mention when talking about Jdox is that Jdox articles are integrated within ETC and APT. So there are certain areas where we can click in the ETC and APT, and this will take us to the related article in Jdox. So this is one of the examples here. If I click on the question mark here, it will take me to the Jdox article that discusses user-supplied spectra. So there's a video tutorial on how to do that. But essentially we need to know that we can either upload an ASCII table that needs to have the extension of dot or txt, and a fits table that has to have the extension fits. For the ASCII spectrum, we need to define two columns, one for wavelength and one for flux density, and the units there should be microns and millijanskis respectively. For the fits table, we have more options, more flexibility about the units of wavelength and flux, but we also need to make sure that all the keywords in the header are defined. Okay, so I will go back to the ETC again. So if we upload a spectrum, the spectrum should appear over here, and then back in the scene and sources and the continuum, I would be able to select my file from this section here. In case I don't have a spectrum for my source, there are different options to describe the continuum. I could use a flat continuum. I could use a power law continuum where I can change the exponential. I could use a blackbody spectrum where I could tweak the temperature. There are also templates for stellar spectra and extragalactic spectra for galaxies. And since I will be giving an example for a star-forming galaxy, I will choose the galaxy spectra from Brown and Tal. And once I do that, right below, you will see I will have the option spectrum from different type of galaxies, okay? And since I will be, let me know if you're still can hear me. I just got a message that my connection is unstable.
Yes, there were a few very short interruptions, but we can hear you. Okay,
that's great. So since I will be observing a star-forming galaxy, I will just go ahead and click and select the option for this spectrum. Since this is a galaxy, it should have a certain redshift, which I should input in the box of redshift over here. Let's say it's 0.25. And it's always important to remember that we need to save for everything to take effect. So right now, this is the source spectrum plots. It still shows a flat continuum, but once I save that, it will show the spectrum that I've chosen from the list above. Okay, and we also have the options to select different extinction laws. If we want to, I will just stick with the defaults. And as I said, we have the option to use template spectra, but these do not necessarily correspond to the exact object we have in mind. So we need to renormalize those spectra to match the attributes, the photometry for the object we intend to observe. So we have the option to normalize the source flux density at a given wavelength or in a given bandpass, or do not renormalize. And typically this is the option when we upload a spectrum of our own. So for the example here, I will normalize in a bandpass. Let's say that my galaxy has 22 AV mags in Spitzer's IRAC 8 micron band. And again, I will need to save that to take into effect.
Alexandros, you
Yes.
made small mistakes in the AB.
Oh, yes, you are right.
Yeah.
Thank you. So I will need to save that again just to make sure everything is working properly. Great. And the next tab here is where I can input a specific emission line. Again, remember, these are template spectra. There might be, let's say, emission lines in the object that we intend to observe. So we need to input that manually, right? And keep in mind, if your object that has a specific redshift that you defined before, your lines should also be input in the observer wavelength. So let's say that in the observed wavelength, I have a line of interest that it's at 4 microns. It has a line width of 400 kilometers per second and a line strength of this. And I will give the line a name. And I will need to click Add Line. So I will need to click the button over here, and I will see that ETC knows that I want to input a line, but the line is not there yet. It should appear somewhere here. I need to save that. So once I click Save, here is my line. My line just appeared over here. I always have the option to update the properties of my lines. I just need to click on the line, tweak any of the options that I want to change, and click Update, as well as remove any lines that I don't want to use. Okay, moving on to the Shape tab. Since I will be observing a nearby galaxy, it's not going to be point-like. It's going to be extended. So I will use the Extended option. And we have different options for flux distributions, flat, 2D Gaussian, Cerseic, and power law. I will just use the 2D Gaussian. So just to visualize how our scene and source looks like, by default it's that, but I have the option to change the parameters. Let's say 0.1 and 0.3. You will see that these take effect immediately. My source's shape has changed, but it's always important to save that. And also I have the normalization choices for integrated flux or surface brightness. If the renormalization that I used before, it's, let's say, megajanskis per steradians and so on. So we'll just keep integrated flux here. And then the final tab is the offset. So let's go ahead and add the second source here to this scene. I will add it. As you will see, it appears at the very center, but I have the options to place it at a different regions. So let's say this is -3 and 0.1. So you can see I've created an offset for a given source, and this is the way I can create as complex scenes as necessary. All right. I will simply go ahead and remove the source right now. And go back to the galaxy. I can also change the galaxy orientation. Again, I need to save. And basically this summarizes how we construct, how we define our scene and sources. So once we do that, we are able to perform a calculations. So we go back to the calculations tab. We have the different options for the different instruments. So let's say I want to do an imaging observation to observe the region where my emission line is. So I would choose NIRCam long wavelength imaging, and it will create a first calculation using some default parameters that we will see in a second. So we need to click on the calculation, and then we will have access to the second section on the right. We can define all the different properties for our calculations. So the first section here, the first tab is the scene tab. And it's basically, if you look at the different tabs here, these are identical with the ones in the scenes and sources. So that means once I finalize the geometry of my scene I can simply go ahead and do all the tweaking that I want for my source using the scene tab in the calculation. So I do not need to switch back and forth all the time. And each parameter I choose, I don't need to save that. This is saved by default. I also have the option to create as many scenes and sources as I want to. And if I want to do a certain calculation for a given scene and source, I would be able to select it here. Okay. The second option here is the backgrounds, where we defined the region where the background will be estimated and subtracted. So we need to give a set of coordinates for the region that our background is going to be estimated. And if we know the date of the observations, we can input that here. Otherwise, we have the option to choose between predefined configurations, low, medium, and high. I will simply go ahead with the default right now. In the instrument setup, I'm able to choose the filter of interest for my science. In my case, since I'm interested in a line at approximately 4 microns, this should be the appropriate filter. And then moving on to the detector setup, we will see all the options that will define our exposure parameters that Loic explained before. So the first thing, I have the option either to use the entire detector, that would be the full option, or otherwise use sub-arrays, meaning smaller portions of the detector. Okay, I would be able to choose my readout pattern here. So right now, all the calculations are performed using the deep 2 readout pattern. Let's see how things change if we choose medium. And one thing I want to mention here is that there are constraints with respect to the readout patterns. That means that certain readout patterns allow a certain number of groups and integrations to be chosen. However, ETC will not give me any warning or error if I go above this limit, right? A quick example would be that if Rapid, if I remember correctly, cannot go above 10 or, excuse me, 2 or groups or 2 integrations. But as you can see, APT allows me to do that. However, when I will use APT and I will input the groups, integrations, and readout patterns, APT will warn me that it cannot, these number of groups or integrations are not allowed. So we can either go and review the readout patterns on Jdox, or we can input these numbers in the APT. So I'll just go ahead and click select a medium 2 pattern. I will leave the default groups and integrations as they are right now. And then I will move into the strategy tab, where basically I define the properties for the aperture that the signal to noise ratio is going to be calculated. I can specify the location of the aperture. So right now, this is the footprint of my galaxy. I would be able to calculate the signal to noise ratio, not just in the center, but at any different point. So I would need to define a specific offset for that. And these are the options for the background subtraction. Okay, so I will just tweak that. I will tell it to calculate the background in an alias between 1.2 and 1.3 arc seconds, and I will hit calculate, and it will perform the new calculation for me. So there is not an optimal way, there is not one prescription to understand which groups, how many groups or how many integrations you need to use for your sign case, but you can experiment a bit and see what is the signal to noise ratio you achieve and what's the exposure time needed for this calculation. And an easy way to do that, you need to first click on your initial calculation, and then you have the option on the top to expand in groups. So right now, I can start from 11 groups because I already have the calculations for 10 groups. And then I can have a step size of 1 and 5 iterations. And once I submit that, it will calculate how the signal to noise ratio changes as I increase the groups. So the calculation above is for 11 groups, 12, 13, 14, and so on. So I can see how the signal to noise ratio changes once I change the groups and keep integrations fixed. So we also have the options to keep the groups fixed and change the number of integrations. So I need to click on my initial calculation, and now I will expand on the iterations. I already know what's the exposure I get and the signal to noise ratio for one group, one integration. I'll start from 2 and go up to 5. And these are the results: 2 groups, 3 groups, and so on. Okay, you see that you're increasing in signal to noise ratio, but also in exposure time as well. All right. On the plots on the bottom, on the images, we can view the 2D signal to noise ratio that we achieve. We can see what's the electron per second in the detector. We can see we have any pixels saturating, and also we can see the groups before saturation. In order to understand that, it's really it's easier if we look at the reports tab over here, where we have a number. It tells us what is the maximum number of groups before saturation. So ideally, I could input 700 groups here and I would not saturate, right? But again, that doesn't mean that this is allowed for a given configuration. ETC does not put a constraint here. You can input that number, but in practice, you are kind of restricted depending on the readout mode and observing mode, okay? And then here I can view the extracted flux from the source. What is the background extracted sky? I can see the signal to noise ratio in a given wavelength and how that changes with the exposure time. And probably this is more useful when we want to compare different calculations. So I have the options to select any calculations I want to compare. In this case, I will just go ahead and select all. And if I move down, I can see how the different calculations give results for signal to noise ratio and with respect to the exposure time. Okay, so here the final tab again has a report for a given calculation that is selected and the given configuration. I can also see if I have any warnings here or errors. And the last thing that I can do is I can download all the images created by ETC here, and I always have the option to load them on DS9 and so on. And this is basically one example, one overview of using ETC, defining a scene and source, and performing some basic calculations for our science. So probably now we will move on to the APT, okay? So we will cover the main features in the APT, okay? And let me know if you can still view the APT right now, because I changed desktop.
Yes, I can see it.
That's great, okay. So the APT is the tool we will be using to define all our observational parameters and submit our proposals, okay? So we have a toolbar on the top with many options. Probably we'll mostly be using the form editor, the visit planner, and Aladdin, and we will see what these things do in a bit. Okay, so I will just go start and create a new JWST proposals and see how we work. What's the workflow from creating a new proposal. So once I click that, we have the tree editor on the left, okay? And probably the first thing you will notice is that I have these red X marks that correspond to errors. And before submitting my proposals, I should correct all these errors, all right? So the first tab that I see is the proposal information. And this is pretty trivial to understand. We need to input the title and the abstract for our proposals. We need to select a scientific category and assign science keywords. And also here is where we are going to attach the PDF file that contains our proposal, scientific and technical justifications. Okay, so I will not spend any more time in this specific tab. I will move on to define a target. So in most cases, I would be using the fixed target resolver to find my target, unless I had a solar system target where the process is slightly different, or planning MSA observations where I would need to input a catalog. Okay, so I will just go ahead and use the fixed target resolver. And I have the option to search by name or position. So let's say I will be observing Galaxy M51. I also have the options to use multiple databases to search my results. So we'll do that now. And you might see that there's a slight difference in coordinates between the two catalogs. This is mostly encountered when we have galaxy pairs. So you may have coordinates centered at one of the two objects, or somewhere in between. And I will just use this case here, which if I remember correctly, it's somewhere in between, right? So right now I have some X marks with respect to my target that I need to correct. The first thing that I need to do is to assign a category, and this is a galaxy. I need to define the description. I know that these are interacting galaxies, so I will click on this tab. And the next thing that is good to provide is whether my source is extended or not. And I know in this case that my source is extended, so I will click on that. Okay, so right now we don't have any red X marks. We just have a warning that tells us that our target is not used yet in the proposal. So I will go ahead and create an observation folder for my observation. And let's say I will do NIRCam imaging. So I will name that NIRCam imaging and edit my observation. So this is going to be M51 NIRCam imaging. I will need to select the instrument, which is NIRCam. The template is NIRCam imaging in this case, and then I need to select the target here, M51. Okay, this is the visit splitting distance that Loic mentioned in his talk earlier. So we also need to keep an eye on what is the splitting distance, and what is the number of visits that we have as we plan our observations in the APT. So these, the number of visits might change depending on the dithering patterns we choose, or if we want to build a mosaic, for example. Okay. So I will go ahead now and discuss and fill out the observational properties for my observation. So the first thing I want to select is if I want to use both modules that NIRCam has, or I also have the option to use just one of them, module B, but I will go ahead and select all. I will use the full subarray, and then I have the options. I need to select a specific dither pattern. Okay, so in case I don't remember or don't know exactly what are my dither parameter options are, I have the option to click on this field here, and this will redirect me to Jdox and read about the dither parameters offered. So I will do that. Hopefully you can follow me here. So this is an overview for the different dither parameters that I get. And I can read and choose which one is the best for my observing plans. So I will just go ahead now and select a full box. For example, I will just use 2 tight gaps and go with the defaults. And it's also good to know, and I will show you now how we are able to visualize the dither patterns just to make sure that they're exactly what we want to do. And a way to do that is by using Aladdin. So if I click on the top bar at the bar here, viewing Aladdin, it will load up Aladdin, which is a different software. Oh, before doing that, I will just need to go back to the form editor. I need to define my filters. So remember that with NIRCam, you can observe simultaneously short and long wavelengths. So that's why you need to define both short and long filters. I'll just select random filters. And here is where I define the exposure time parameters that I used in EDC. So I would just go ahead and select a medium readout pattern, let's say 10 groups and 1 integration. Okay, so I have no more X marks here. I also have the option to give the ID workbook that I worked before in the EDC here. Okay, and what's left is a warning telling me that I need to run the visit planner to tell me if my observation is schedulable or not. But I will not do that just yet. I just want to show you how you can visualize the different parameters. So we have a lot in here, and now you can see the footprint of NIRCam, but we cannot see our galaxy yet. So in order to do that, we either need to be viewing Aladdin, and then we have the option to load a DSS image. It will load a black and white DSS image, or we have the option to select a different image from Aladdin's panel. So I will just use DSS. It will load a colored image of the galaxy. And you can see indeed that these are not centered in one of the two objects, but we can fix that in a second. I just want to show you how we can visualize the dither parameters. So going back to the form editor, if I change from the full box to a full dither parameter, and then maybe choose 3 tight, this is how I could be able to see how my dithering parameters are right now. And right now you can also see that the number of visits has changed from 1 to 3 just by changing, defining a specific dither parameter. I will just go back to the full box again, 2 tight gaps, and this is what I get, all right? Again, going back to Aladdin, as you can see, if I'm not exactly happy with where my grid, where my field of view is centered, I have the options to change that. So just making sure that you have your mouse showing this finger, and then once I click that, I'm able to drag and center it to a new location. And you will probably observe in the APT that now it tells me that I have pending changes. So I'm able to move from my initial coordinates to the newly defined over here. And I can do that if I click on commit all. If I'm not happy with that, I could also revert back and select clear all. But since this is much preferable, I will select commit all. And now APT knows that the new coordinates are set in this region here. I also have the option in Aladdin to rotate the field of view. I would need to select the orient ranges here, and I can visualize how my apertures would change once I rotate them, okay? In this particular case, which is a face on galaxies, we don't have a specific orientation preference, but we can just visualize how the rotation would look like in Aladdin, okay? However, in this case, we don't have the option to automatically commit this change as we did with the change in the coordinates. If we're interested in setting a specific position angle requirement, we would do that. If we go back to the form editor, there is a specific tab for special requirements. And once I get there, I can add different requirements. There's one, for example, for timing. I might want my observation to happen after a specific date, or before a given date, or after a specific observation. One of the frequently encountered requirement is a position angle requirement. And here is what I discussed just a second ago, that I need to set the position angle range that I'm interested in here, all right? And it will ask me to either use the aperture position angles or use the telescope V3 position angle range, all right? I will need to set that here in order to take into effect and be registered in the APT. I will not use a special requirement, and now I will just go ahead and remove it. The next thing I want to mention is basically how do you build a mosaic. So let's say that I want to cover the bright portion of this galaxy over here. I will need to go to the mosaic tab where I can tweak the mosaic properties. And by changing the numbers of rows and columns, I can create more tiles and build my mosaic. So let's say I would use 4 rows, right? This is probably more than enough. Let's try 3, okay? And right now I've built a mosaic that will cover my galaxy. I also have the options to tweak the overlap between the different tiles, or shift rows and columns, and these are defined here, okay? Right now, since we built a mosaic, you will see again that the number of visits has increased to 6, all right? So this is also a thing to keep in mind. And probably the last thing that we need to check is if our observations are schedulable, okay? So in order to do that, we need to select the folder or the observation that we need to check, and then go to the visit planner. So once I do that, okay, the visit planner, I will click the update display, and the visit planner would check all the parameters that I input, all the requirements and restrictions, and see whether my observations can be planned within a given cycle or not. So we'll go ahead and click update display. And in a few seconds, hopefully this will turn into a green check mark, and it will tell me that the specific target, the specific mosaic, and with the specific requirements, which in this case, we do not have any constriction, is schedulable, okay? You can still see a warning here, but this is kind of like a bug. If you click again, it goes away, all right? And I can look at any reports for any of the different visits here. Let's look at the total analysis row. So here, I can see which position angles are going to be observed at given dates for this specific object, and for how many days a given position angle is viewable, okay? This is basically what you would get, one of the tables and figures you would get if you would use the general target visibility tool. However, in order to be able to use this within the APT, as we did right now, you need to first go ahead and define your target, your observations, and run the visit planner. So if you want to know before that, that's why you need to use the general target visibility tool. It's much easier to use. You just type from the terminal the coordinates of your object, and you can get basically this plot and this table, right? And I think this sums up the overview of the APT, how we would define a target observation, how would we use the main features in Aladdin, run the visit planner, and make sure we have no errors before submitting our proposals. So yeah, I will stop here and let me know if you have any questions.
Thank you very much, Alexandros. That was very clear. A comment or question about the mosaicing. You know, a good practice is probably to set, the first thing to do is to set your position angle before building your mosaic.
Right.
Because otherwise, if you don't set a constraint, the mosaic angle will be different. It could be rotated without you noticing that that's what's going to happen. So I think a good practice for mosaicing it would be to set a PA first. So is there any question for Alexandros? So Don't be shy. Don't be shy. Otherwise, if there's no further questions or comments, what we'll do is stop for the morning session and reconvene in the early afternoon at 1:30. Yeah, and essentially the first hour and maybe up to an hour and a half of that afternoon will be again slide presentation. So and then you'll have the rest of the afternoon to do some practice at home. Obviously the format is different than initially anticipated, initially planned. We had planned to be next to you and be going through screens, each individual screen, and be go around the room and help. So this is going to be different. So we'll see how it goes this afternoon. Yeah, so if you have no other question, so the recording, yeah, good question, Lisa. So there's going to be a recording of this morning session. It's currently being saved on the Zoom webpage, and I'll download it and make it available I'll probably send an email to the group of people and put the link to that in our James Webb jwst.astro.umontreal.ca page. And Rirtian has a good comment. People interested in the IFU mode and the long slit mode or TSO mode can come in this afternoon. If none of those modes is of interest to you, well, then the rest of the day is free. And otherwise, we'll start with TSO mode slides. If you don't want to hear anything about IFU or long slit, then you can directly go to your exercise and stop listening to the presentation. Otherwise, it's going to be TSO, long slit, and IFU in that order. And you can split at any time you want. I guess that's pretty much it. I have tons of croissants and nice lunches here sitting on my table that I will have to eat by myself. Unfortunately, I have saumon fumé, like salmon, and it's all fancy stuff. So I'm sorry, it's all for me. So yeah, I hope you have a good lunch, and I hope to see you again at 1:30. Thank you, Alexandros.
Thank you.
Have a nice lunch, all.